Hello, and welcome to the first video on useful and common circuits. The first is the voltage divider, and we're going to have two examples for that one. And we're also going to look at the current divider, but just with one example of use. So what is a voltage divider? A voltage divider is two or more resistive components in series with a voltage source. We know that voltage supplied to a circuit is split up proportionally between the components that are in series with each other and the source. So if we care about the voltage across resistor X, we can use Ohm's law to determine the voltage drop across resistor X is equal to the total circuit voltage times the proportion of resistance that resistor X is contributing. So basically, if it's VI is supplying 10 volts and resistor X is 7 ohms and resistor Y is 3 ohms, we know the total resistance is 10 total ohms, where resistor X is providing 7/10 of that total voltage. So logically, 7/10 of the input voltage, or just 7 volts right now, is going to be dropping across resistor X. This is a very simple circuit, but it provides some very useful tools. And the first one is a voltage divider used as a level shifter. In this class, we're going to be using Arduinos to control many of the circuits we're going to be building. And Arduinos can take an input signal with a max of 3.3 volts. Any higher is going to damage that port and possibly the Arduino itself. But many of the signals we're going to be using are a 5-volt signal. And so to protect the Arduino, we're going to use a level shifter to shift the maximum voltage of our signal down to an appropriate level. For an example, let's look at something that's sensitive to temperature using a thermistor. A thermistor is a resistor that changes its resistance based on the temperature. Every resistor sort of does this, but a thermistor is really sensitive to a change in temperature and can change quite a bit based on even day-to-day changes in a room, like from 20 degrees Celsius to 21 degrees Celsius can see a very large change in the resistor value. So we're going to be using an output from a thermistor to check the temperature and input that into a Arduino for calculations to try to control something else with. If we just plug the thermistor from the 5-volt output of our Arduino into the input there, the green one, it's always going to be supplying 0 volts to the system, right? Because it's got all of the resistance, all of the voltage is going to be dropped across that one resistor because it's all there is in the circuit. And we know that if there's only one resistor, all of the voltage has to go down across that resistor. So you have to split the circuit, the resistance of the circuit, into 2 different resistors and then take a value not from the endpoint so that you don't have 0 volts all the time. But this can cause a problem because if we choose the other resistor kind of naively and arbitrarily, we can wind up with more than 3.3 volts going into our input because you start with 5. If you don't drop at least 1.7 volts across the thermistor at all times, you can damage the Arduino. So if we know that our thermistor has a minimum voltage, a minimum resistance, sorry, of 1K ohms or 1,000 ohms, then we need to calculate how much resistance the other resistor needs to provide. So we use our divided voltage equation, where Vx in this case is that 1.7 volts we need to drop across, and Vi is the 5 volts supplied overall to our circuit. We don't know the value of resistor Y we're using quite yet, but we do know that our minimum value of the thermistor is 1,000, so Rx can sub in 1,000. And then if you follow the math there in the orange box, you can see that we come up with a nice equation that'll tell us what value resistor Y needs to take. And the blue box tells us the answer, 1941.2 ohms, which means that even at the lowest possible temperature and the lowest possible resistance that we can use on the thermistor, we'll always drop at least 1.7 volts to protect our Arduino from damage. Another common voltage divider is the R2R resistor ladder. This resistor, the resistor values are always R and 2R, or 1,000 and 2,000, 2,000 and 4,000, either way. It's just important that resistor R is one value, and then 2R is double that value. And this circuit is used to convert a digital signal into an analog output. So remember that digital signals are either high or low, and there is no gradation beyond that. You're either at a high or a low point, on or off, that's it. So in order to get some kind of gradation between on or off, we can use this circuit. So there are two very nice things that are developed by the arrangement of the resistors of this. And the first is that the total resistance as seen by the output voltage lead is always just R. So if you split this circuit into branches, into bits, and you work your way down, you'll see that each branch reduces to just R. The other very nice facet of the voltage divider is that the output voltage is very simple to calculate. If we take each B as a bit being on or off, the total output voltage provided by that bit is determined by how far away it is from the output voltage in powers of 2 to the n, where n is the number of bits it is from the output. So it works similarly to proving that the total resistance is just R, where you take individual segments of this ladder and then you calculate the resistance. You make a Thevenin equivalent circuit. And after you do that, you see that you wind up with a voltage source of V high over 2 in series with all the remaining resistors that are not branched out with the 2R. So if in this circuit right here, B0 is the fourth one, so it's going to be V high over 16, 2 to the fourth. And the pattern continues. So if B0 is on and B high is a value of, let's call it 1 volt just to make it simple, and all the other bits are off, voltage output is going to be 1/16 of a volt. But if we turn on B3 and all of the other bits are off, then we are going to be providing a voltage output of 1/2 a volt. But if we turn on B3 and B0 at the same time, we have a 1/2 a volt and 1/16 of a volt. So we're going to get a total output of 9/16 of a volt. So you can kind of finely control how much output you're providing here based on a digital input signal. And then finally, a quick demonstration of a current divider. It's a very simple circuit, very common. It works on the same principles as the voltage divider, except now we're in parallel. And we know that the total current is split proportionally based on the values of the resistor on each path. We know everything in the universe is lazy and follows the path of least resistance. So the resistor with the lowest resistance will get most of the current until that resistor gets too crowded, and then the remaining resistance will then be forced to go down to the next resistor, which is going to be higher. So a practical use for this circuit is protecting sensitive devices. Many gadgets and gizmos can only handle so much current before breaking down. So it's important to be able to shunt excess current away. So by placing a resistor in parallel with the device or load in question, we're going to be able to ensure that some current goes through the new resistor. And if we know the resistance, the total resistance of our load circuit, then we can actually calculate exactly what value resistor to place in parallel with it to ensure that enough current is taken away from our sensitive device. All right, well, that's all for now. There's going to be some more of these. Hopefully every week I'll be able to post a useful circuit or an applied circuit that demonstrates at least one or two aspects of something we've learned so far. All right. Well, that's all for now. Thanks for listening.